Afternoon, everyone. I'm Yikun from Shanghai Jiao University. Today, I'm glad to introduce our research on the seasoning mechanics of the magnetoelectric effect and its application in structural deformation measurement. My presentation is divided into 5 parts. First, I will briefly introduce our lab. Our research group is part of the State King Laboratory of Mechanical System and Vibration of China. Our main interests include vibration analysis and control, system dynamics, intelligent mechanical systems, and precision manufacturing. Next, I will introduce the background of this work. Large-scale structures, such as aircraft wings and the shafts, are subject to the complex loads will produce the deformation. When the deformation exceeds the permissible range, it may need to measure accidents, such as the wing is a break edge. So it is necessary and important to study the structural deformation sensors with high accuracy and high robustness. Our solution involves the research of the sensors based on magnetoelectric effects. Of course, Wu's presentation also describes this effect. Okay, but this effect have some problems. Now, the single phase materials, because it's small coefficients at room temperatures, making the difficulty to application. Now, the composites based on the product effects of smart materials are widely used. Although this composite have been successfully used for magnetic field and current sensing, but its lack of precision deformation and other mechanical measurement applications. Besides, the modeling of the nonlinear multi-physical field coupling of the sensing mechanism is not perfect. Okay. So we do some work on these 2 issues. First, we do some work on the sensing mechanism modeling. Specifically, we design this mechanical constrained magnetostructive and piezoelectric composite. On the simplest conditions, we can use the linear constitutive equations to get the linear magnetoelectric coupling model. But under the high frequency conditions, we need to consider the structural dynamics. So we can derive the impedance equation of the material, and then we can obtain the equivalent circuit model. Based on this circuit, we can determine the sensitivity simply. Okay. We further take into account the nonlinear behavior of the material, especially the nonlinear of the magnetostructive phase. We have established a nonlinear model for the magnetomechanical coupling. Based on this model, we can derive the equivalent nonlinear constitutive parameters. We can observe that these parameters is related to the magnetic field and the strings. Using these parameters in the equivalent circuit model, we can analyze the nonlinear dynamic behavior of the composite. Okay. The prediction of the piezomagnetic coefficients of our model is similar with the experiments with art in the literature, and we can observe that the resonance frequency is shifted under the influence of the magnetic field and the pressure stress. Based on this phenomenon, we can employ the resonance sensing method to detect the static or slow varying physical quantities. Based on this seasoning mechanism, we design a seasoning scheme for the structural deformation. We convert the slow change deformation into a change in the DC magnetic field. According to the frequency shift seasoning mechanism, under a fixed frequency AC magnetic excitation, the response voltage will change. So ultimately, the structural deformation will be measurement. And they are also given a schematic of the experiment setup. A permanent component is installed in a beam, and the magnetoelectric component is mounted in a platform. These two components is formed a closed magnetic circuit. So the magnetic field strength acting on the composite is dependent on the air gap. When the beam is deformed, the air gap is changed. So according to the structural deformation seasoning principle, we can use the change of the response to measure the deformation of the beam. Also, we also can combine the equivalent magnetic circuit and the equivalent circuit of magnetoelectric composites to form the whole model of the sensor. Okay. Next, we implement a sensor prototype and conduct the performance testing. This is the prototype of our sensor, and this is the experiment setup. The response of the sensor is occupied by the lock-in amplifier, and the deformation of the beam is imposed by a standard wind on put it on the beam. The tested resonance frequency of our sensor have almost 5% error with the zerotic value, but it also means the established model is effective. And we tested the noise. The noise is smaller than 7.5 nanovoltage. Okay. We analyze the attractive force between the two components by using the FEM method. It was found that the influence of the attractive force can be negated when the air gap is not than 6.5 millimeter. So, when set the initial air gap is 8 millimeter to conduct the measurement. The time history of under different nodes and at three different excitation frequency, we can find that our sensor can respond quickly and coincident to each node. And the sensitivity curves shows that it have good linearity, and we can find that we can obtain the best sensitivity when the excitation frequency is near the resonance frequency. Considering both the linearity and the sensitivity, the optimal initial air gap should be 8 millimeter. And we measure the repeated 4 nodes for different mass. We can find that the standard deviation of the response is smaller than 1 microvoltages. It indicates that the system have good repeatability. Limited by the minimal mass of the standard range, we have recently achieved a minimal deformation detection of about 800 nanometers. Then, we applied the sensor prototype to detect the static deformation of a sharp shift. The deformation of the sharp shift is applied by a hadronic actuator, about 40 tons. The result indicates that the sensor has high accuracy and repeatability. Finally, let's summarize this work. Accuracy magnetoelectric electrical coupled sensoring mechanism model is established, and a sensor prototype is realized for precision structural deformation detection. Further, we need to do some work for the temperature characterization and to compensation the temperature effect. Thanks for your attention.